So hello everyone, this is lecture 19 for electricity and magnetism. In the last lecture we have completed the motion of charged particles in the electric and the magnetic fields, and today we will start the magnetostatics. And what we will study here, we will study the magnetic field due to a steady current. So we will study all about the magnetic field which is due to steady current. So let's start. First it is the current in a wire. So you know how the current is defined, that is dq by dt. So if there is a single wire and current is flowing with velocity v, then what is the current can be defined if the charge density is lambda. The lambda v will give you the current. How? Because this is length per unit time and this is charge per unit length, so it will give you total charge divided by time. So that will give you dq by dt. So you can define your current in a single wire this way. Now see, in the one dimension the current and the velocity in the same direction, so that's why we just represented by scalars. So I equal to lambda v. So current is scalar in one dimension. So in general it is vector, but we can write it as in this form in the single wire. Now see, this was a case of single wire. Now the current can be in the surface area also. So this is the surface you have. Now current is flowing in this, means the current in this direction. So there will be di current in this particular small region which have the width dl, and this is perpendicular to the current. Now see, in this small length the surface current is defined as this current, this complete current per unit length is defined as the surface current. So, and the surface current can be written as sigma v, where sigma is the charge density per unit area. So it is charge per unit area, charge multiply length, and length will cancel out the one length, it will give you current per unit length. So just units will be same like this. So this defined as the surface current, means the current per unit length in this particular region, that will give you surface current. Now same is, you can have this volume current also, means now there is a solid thing and you have a small volume. Let's assume this. Now this cuboid, the current will be passing through this complete surface. Now the current per unit this surface, per unit this area, is called the volume current, or the J, or the current density J, that is current per unit area on this one. And this can be represented by rho v, where rho is the charge density, charge per unit volume. Now this unit will be length, and length will cancel out, will give you area unit. So this unit will remain same as this. So your current, volume current defined in this way. So you must remember all these formulas. Like there is example, you have this surface which is making the n cap angle, means n cap is this direction, and this is the direction of the current, and this is the angle made by this. So the total current from this surface is given by this formula J dot dA, where this is current per unit area and this is area. So this dot product will give you your projection of the current in this way. Like you have find the flux, that is the same case, but now here you are finding the current. If this area and this current is in the same direction, then theta will be 0, so it will be simply J dA, I mean current per unit area, and the complete area will give you total current. So you must remember this formula for the solid. So that's how you can find the current in a solid surface. Now there is a case we studied that there is a charge moving in the uniform magnetic field, and it feels a force. Now if there is a current carrying rod and it is placed in some magnetic field, then it must also feel some force. So let's find that force. So if there is some dl element and this current is flowing in this rod, and on this dl length, then there will be some charge that will feel. This is the external field which is coming outward in this whole region, and this rod is placed in this. So we need to find the force on this small dl element, and we need to generalize for the complete length. So dq will be lambda dl, charge per unit length, multiply this dl will give you total charge moving, and charge, and we know from the Lorentz formula q v cross b. So dq v cross b, in place of dq will write lambda dl v cross b. Now see, this lambda will go inside, and lambda v cross b, and lambda v is nothing but this is the current in a wire, this we already defined. So this I cross b, and see, in the one dimension we defined I in the same direction as dl, and we defined it as scalar, so we just put the vector on the dl because they are in the same direction. So the force will be I dl cross b. So this is the generalized formula for the rod, current carrying rod inside a magnetic field, that is equal to I dl cross b, this line integral. So this will give you a total force on the line carrying means current carrying rod or the in the magnetic field. So you must remember this formula. Let's now in the surface, means this, now this is not a rod, there is a complete surface, 2D surface there in the magnetic field. And what will be the force? So again q v cross b, and q charge is given by sigma dA. So this will be equal to, you know, this sigma v is nothing but k cross b. So this will give you sigma will k and k cross b dA. So this we already find it here. Sigma v is your k. And for the volume, now again you can apply the same logic. This will give you j cross b d tau for the 3D surface. These are the forces felt by the current carrying surfaces due to the external magnetic field. Now let's take an example. You have this current loop, single rod and current loop, and you need to find this is a uniform magnetic field which is going inward. So you need to find the force on this. So first we will separate the lines. First this one, this one, this one. So for this first rod, it will be I dl cross b, and dl is in this direction, b in this direction in the inward. So angle is 90. So it will be dlb simply, and dl this complete length, let's say a. So it will be ib dl will give you iba. Now this magnitude of force will remain same for this because it is a square shape. So this will be length a and a. So magnitude will remain same, but see direction for this will be in this direction, and for this it will be in this direction. Using the right hand thumb rule you can find the dl cross b. So dl is in this direction, b is going inward. So dl cross b will give you this direction of force, and for this. So net magnitude will be 0 because this will cancel out this one and this will cancel out this one. So net force will be 0. So this is a general case. For any loop, it can be symmetric or unsymmetric. There will be a complete magnetic force will be 0 always. Means this current on this loop, the F net is always 0 for any loop in the uniform magnetic field. So you must remember this result. Now let's say if this is not a loop, it is an open thing, open wire, or it can be anything. So let's say we have this open wire and this carrying the current I. This is the position 1, this is position 2, and we need to find the force on this wire due to this uniform magnetic field. So how can you find? So just assume a single rod from this initial point to the final point, and just find the force on this single rod, and that will give you the force on this complete wire. So this will be, let's take it out, it will be like this. So it is again dl in this direction, b is going inward, so force in this direction. This will give you the complete force, and magnitude will be ILB because angle is 90, current is I. So this will be your magnetic force on this complete wire or anything. So let's take another case. You have a semicircular wire or the loop. It is not a complete loop, it is just a semicircular wire. You need to find the force on this due to this uniform magnetic field. So again assume the initial and final position and take this out, and this length is 2r because this radius is r. So again I dl cross b will give you ib 2r. So this will be your force on this complete wire. So just remember this trick, or this is not trick, this is a very basic thing. Now we are studying the steady current, so we must understand what is steady current first. So general condition for the steady current. So first we will study the continuity equation. So let's say we have some volume. This is some volume which has the surface S, and there is a charge going outward. This is a charge carrying, means this volume carrying the charge, and this charge is going outward from this volume. It is going outward. So the charge density is decreasing inside the surface or the volume. So let's see what is the current if this charge is going outward. Then this current will be the sum of all these. So total current through the closed surface. So this is a closed surface S of volume V. So total current will be J dot dA, and the closed integral means for the whole surface we will take. This is the current per unit area, so it will give you current, and for the whole surface we just integrate this. For whole surface we have find the current. Now, so this IT shows the total current. Now using the divergence theorem, we can just write it in this divergence of J. This can be written in this form, and this is the volume integral. And see, the current is nothing but total charge going outward divided by time. So total charge is volume charge density is rho. So it is rho multiplied by d tau will give you total charge, and dt will give you the current. And see, this charge is going outward, so density is decreasing inside, and this current must be positive. So we have just put minus sign outward to make it positive. So this is the formula, and now these we can compare these two things. So del dot J must be equal to minus del rho by del T, and this del rho by del T represents the rate of decrease of charge. That's why we have presented negative sign here. Now see, this equation is called the continuity equation, and this represents the local conservation of charges. And see, now see that charge is going outward means divergence is positive. So see, this density is decreasing, so it will give you negative sign. So ultimately it will be positive. So for charge going outward, divergence is positive, and that is what divergence represents. Now see, if the charge is coming inward, then it is converging, charge is converging. So this will give you the positive value, and this complete divergence will be negative. So that's how you just can see the property of divergence. Now, what is the steady current? Means if this kind of situation you have, then this current can't be steady, because if charge is decreasing or increasing, means here or here, then it can't be steady current, because steady current means the constant current. So to make it steady, this charge density must be remain constant, and if it is constant, that this term becomes 0, because this is not changing with time. So this will become 0, and this divergence of J will be 0. So this is the basic condition for the steady current. Means if divergence of J is 0, only then you can say that current is steady. So you must remember this condition. Now let's start the Biot-Savart law and superposition principle. So what is this? This law is used to find the magnetic field at any point due to a current carrying wire. So we can find that using a wire also, using a surface also, and via volume also, volume carrying the current. So just let's find first from the current carrying wire. So there is this point which is at the r vector for this, and this current is going in this direction. So Biot-Savart law says that magnetic field at this point will be given by mu naught I by 4 pi dl cross r cap, and r vector magnitude square. So the r cap is given by in this direction, same direction, and I in this direction. So dl will also be in this direction. So dl cross r will give you the vector in the downward direction going inside the paper, the magnetic field. So just using this you can find the direction of magnetic field also. And here mu naught is nothing but the permeability of free space, and mu naught, the value of mu naught is 4 × 10⁻⁻⁷ in mks unit. Now this is the case for a wire. If there is a surface carrying the current, then this I dl cross r will be removed by, we already find these expressions, k cross r dA, because here you have the r, so that's why it will be k cross r dA. And for the volume it will be removed by j cross r d tau. So for the volume is this. So remember these expressions for the surface, 2D surface. This will be an expression for the magnetic field at any point r, and this will be for the volume, from the volume at any point r. Now we can write in the coordinate notation also. What is the coordinate notation? So you have some source. This is your wire or volume or the surface. This is your source, and you need to find the magnetic field at any point which is at r distance. So I am representing this by small r, and the source as r dash. So whatever relating with the source is represented by the dash, and this is the r vector where you need to find the field. So this will be equal to mu naught by 4 pi, and this j at r dash means what is the charge density at the source, multiply the r cap will be this direction, and d tau dash is a volume element of the source. So this will be the case, and this is the representation at r. Means from the coordinate axis at r vector, what will be the magnetic field will be this. So and b dash is due to this source, so that's why I am representing this. And r is nothing but x y z cap, and r dash will be x dash y dash z dash. So you must know these things, very important. Now let's move forward. Let's see some examples. Let's first find the magnetic field due to a finite wire. So there you have the finite wire, and this length is L, and this small length element is dl. We need to find the magnetic field at this point due to this complete length. So we use the Biot-Savart law for the single wire will be this way. So first we need to find this dl cross r, then we can substitute the values. So dl cross r is nothing but dl sine alpha, because here the magnetic field is due to this wire, it will be going upward here and going downward here, something like this from the right hand screw rule. So the dl element is here, so they will be perpendicular, so angle between them will be 90. So dl r, so forget the 90, here you need the angle between dl and r. So dl is going in this direction, r is here, so angle is alpha, so it will be dl sine alpha, and r cap, this is the unit vector, so magnitude will be 1. So dl sine alpha, this is your dl cross r. Now first let's find the dl. So how can we find the dl? First let's see that this angle is theta, this is alpha, so tan theta will be L upon d. Now from here dl will be d, tan theta will give you sec square theta d theta. So you have now the dl, and alpha is nothing but 90 plus theta. So sin 90 plus theta will give you cos theta, so it will be dl cos theta, and dl is this, so d sec square theta d theta cos theta. Now 1 upon means sec theta will cancel out 1 cos theta, it will be d sec theta d theta remaining. Now cos theta equal to d upon r. D upon r. From here this 1 upon r square can be written as cos square theta by d square. So just 1 upon r square is value this. So we'll substitute here 1 upon r square, and dl cross r will be this. So let's substitute all these values in the expression, final expression. So it will be mu naught I by 4 pi, and this is your dl cross r, and this is your 1 upon r square. Now 1d will cancel out, it will came out 4 pi d mu naught I, and this will be only cos theta remaining. And now see, first let me show you this case. This is your finite wire, and you need to find this magnetic field due to this complete length. Then this angle will be theta 1 from here, and this angle will be theta 2 from here. Then you have to substitute limit here, theta 1 to theta 2 for a finite wire. So this is a general case, and so this integration will be sine theta. So it will be sine theta 2 minus sine theta 1. So this is your magnetic field due to a finite wire. Okay. Now this phi cap, what this phi cap represents? See, this current is in this direction. So this magnetic field will be coming outward from here and going inward from inside here. So this direction of magnetic field is changing around this wire at every point, and it is changing like the phi cap. In the core you have the spherical coordinate system. So there you see that phi angle is changing at every point. And if you just take this wire as a standing wire, so you will see that phi is changing according to this. So that's why we can just represent B with the phi cap, because it is changing direction at every point around this wire. Now this is a general case. Now let's see this result in the other cases also. How can we apply this? So in the infinite wire, this wire is infinite. So this at infinite, we will assume that this angle is nothing but 90 degree, and this at this infinite end, this will be again 90 degree. But see, this is the anti-clockwise, so it will be positive, and this is clockwise, this will be negative. So theta 1 is minus pi by 2, theta 2 is plus pi by 2. So just theta 2 will be pi by 2 and theta 1 minus pi by 2. Substitute here. You will get 2 here, and 2 will give you mu naught I by 2 pi d phi cap. So this is your magnetic field due to the infinite wire. So you must remember this result. And now see this is your wire, this is your magnetic field. So at every point the direction is changing, and it is in the direction of the phi cap. Now we can also apply this result in the semi-infinite wire. So semi-infinite wire means one end you know and the other end is you don't know. So that is going to infinite. So initial angle theta 1 is 0, but theta 2 is pi by 2. So substitute here theta 2 pi by 2, and this is 0, so it will give you 1 here, so it will be mu naught I by 4 pi d. So this is your magnetic field due to a semi-infinite wire. So must remember these results. Now there is the last topic for today. That is two very long wires there which are carrying the current, steady current I1 and I2. You need to find the force per unit length on each wire. On each wire means first you need to find the force per unit length on this wire due to this, and then you need to find the force per unit length on this wire due to this. So there will be a magnetic field around this wire due to this wire, and this wire is carrying the current, so there will be force on this wire. So let's find that force and per unit length. So first, so this is the infinite wire, so we already find the what is the magnetic field due to an infinite wire. So that is B1 will be given by mu naught I1 by 2 pi d. So this is the magnetic field produced by this wire around this. And now what is the force field by this wire due to that magnetic field? So force is nothing but I L cross B. So this length is DL2 and cross B1 and I2. So this angle is 90 degree because this is going inward magnetic field and this is going this word, so angle will be 90 degree. And see this DL and B is going inward, so right hand screw rule will give you force in this direction on 2 due to 1. So I2 B1 and DL2. So you need to find the force per unit length. So this will go this side. So force per unit length is represented by F21, that will be F21 divided by DL2. It will be equal to I2 B1. Now substitute the B1 value here. It will be mu naught I1 I2 divided by 2 pi d. Now this is the force per unit length applied on this per unit means this wire per unit length. Now we need to find the force per unit length on this wire due to this. So again we need to find the magnetic field B2. So B2 will be nothing but mu naught I2 by 2 pi d. So that will be the magnetic field produced by this on this, and that will be coming outward because this current. You can use the screw rule again, and this is the magnetic field direction. So this means how you can find the magnetic field. So L cross B. So L is in this direction, B is in this direction. So it will again give you this direction of force because L cross B will be this way. So this is your force on this wire due to this wire. It is again in this direction. So let's find the magnitude. So on the 1 due to 2, it will be I1 DL cross B, and it will give you DL will go this side. So it will be I1 B2, and B2 is again B2 will be mu naught I2 by 2 pi d. So it will be mu naught I1 I2 2 pi d, because I1 is already there. Now see, this force per unit length on the 2 due to 1 and force per unit length on 1 due to 2 is same. So this force per unit length will remain same. And see that for the same direction of the current, they are attracting each other, means force are in the same direction. And if the current is in this way, going in this way, then again the force will be in the same direction, means attracting each other. But if you will see that they are in the opposite directions, the current, then the force will be like that these wires are repelling each other. So this is the case. You can just generally see the direction using the screw rule. You will see these directions, but force point length will remain same in all the cases. So that's all for today. Thank you everyone.